Uh, yeah. Thank you for the kind introduction. My name is Onur, and I'm the winner of this competition. Like, who gets to have like title which is the longest? And even when I changed mine, I slightly shortened it. It's still the longest. And I'm a member of like Lesser group in Tulane. I wrote Glasser in comic sans because, like, as you might going to see, this is going to be the ugliest presentation because I had to do it like very slow, like quick and dirty, and I put function before the form, and there are lots of handwriting. So first, I'll be talking about mode decomposition, and I'll be going through some physical and computational technicalities because it took maybe a year of mine just to figure this out. So I think the new researchers could benefit from it. And second, I'll be talking about basic classical diffraction theory of like apertures of like for paraxial beams, but in terms of like this mode decomposition theory, such that like I'll be talking about some matrices which represent like the interaction with like spatial mass or turbulence, and then I'll be talking about some special type of paraxial modes called self-healing modes. And third, I'll be talking about what we are doing in the lab, basically, and then which is being like seeded four-way mixing. So it will be phase-insensitive amplification, parametric amplification, but I'll be talking about how it's going to be effective if we use structured pump. And so first I'll be talking about like semi-classical treatment, and then go over the full quantum treatment. So Paraxial approximation on first, for light propagation or any electromagnetic field, we have Maxwell equations, and you constrain it. You have like you have a light beam which is heavily polarized in one regime. It becomes scalar Maxwell equation, and then you further make approximation, becomes Helmholtz equation, and later, if your beam is constrained to a beam like a ray or something like that, so it's not divergent far away from Z, then you end up with paraxial beam equations, which is just a diffusive equation, like, or it's also called optical Schrodinger equation. And it has these eigenmodes in Cartesian coordinates is like Hermite-Gauss modes, which look like this. For 0, 0, you have like a fundamental Gaussian mode, and then you have all this higher order modes. And for if you solve this in cylindrical coordinates, then you have this Laguerre-Gauss set. But this, yeah, and they look like this. So as you increase the P index, you get like, it looks more and more like a bullseye pattern. And if you increase like the L, you introduce some topological singularity or OAM, and then like, so at the end you get this dot in the center, which becomes a vortex. And the reason why we are talking about this is basically physical. So because I'll be mostly talking about like the multi-spatial mode, but like usually like when we talk about what is the fundamental basis, fundamental block of this, of like single mode of light, we usually think it as these pixels. And even for like image processing, even when you're not talking about this paraxial propagation, you could decompose like anything, for example, in terms of this pixels, right? This smiley face composed of many, many of these pixels. But if you were to propagate this pixel, then like this this supposed fundamental block actually diverges, so it's not shape invariant. So it might not be the fundamental basis of this problem. Likewise, you could use these angles to decompose this, which is actually your Fourier analysis, and your just thin lens, ABCD thin lens, basically decompose your beam, for example, into all these angles. But still, like this wavelets of like Fourier transform, like all these angles, also they they diverge when they are propagated, and then like they don't preserve their shape. But these fundamental eigenmodes such as Laguerre-Gauss, Hermite-Gauss, when they are propagating, like they get larger and larger, or like when they go through like this A, B, C, D elements such as thin lens, they just change their shape. Sorry, they just become larger, but like they maintain their shape. And then like you can decompose this smiley face, since these LG beams being orthonormal set. Basically, you can decompose them, and then like once you add them back up, you get your smiley face back. But there needs to be some concerns, like because there are just two parameters you need to choose when you are decomposing anything in Laguerre-Gauss, which is being this beam-waist parameter. So it means like in this waist plane, how large it's going to be, and also like the focal position of this. And then like if you choose this, then you can decompose anything like in any 2D data which is used in image processing too. But in our case, any electric field in that. And one technical issue is that like how we are going to choose this is actually like in this paper, like people show like without using any a priori scale information, just from looking at the propagation of the intensity pattern alone, you get this m square beam quality factor. And just by using this beam quality factor and then like your usual beam waist from your intensity pattern, you could choose this fundamental LG basis beam waist for given beam, and solve it. Also, another technicality is that like when you are trying to compute this, usually you can't use infinite sum of modes, and usually like only a finite couple of them affects this decomposition. So you truncate to like some maximum L max, some maximum P max, and for this presentation, and I just use an ordering and then use a single index S, such that like you are bounded by some S max on finite amount of modes. And another concern is that like if you are once you are trying to simulate this, you need to sample this on some numerical mesh grid, and even though these LG functions are extending infinitely, you can just limit to a spatial extent, like for Cartesian maybe X max and negative X max, and for polar grid maybe up to some R max. And also, just like the discrete Fourier transform, as you are sampling this, you need to be careful about the LG HG equivalent of Nyquist sampling theorem. So for example, if you are trying to take Fourier transform, if you haven't sampled enough, you won't get accurate results. That's why like you need to be using a ton of grid space. A ton of grid points while when you are discretizing the this LG HG discretization problem. And having done this, you could use your favorite data integration method on a given mesh grid, like such as Simpson's one-third rule, trapezoid rule. This is one kind of method. Or you could just use least square regression, such that like, I mean, this is especially good for if you are doing for intensity patterns. And at the end, your whole beam or your whole picture is just represented by a vector of like coefficients for given parameters. For example, this is my cat. I just decomposed it into some indices and then like added them back, and then voila, just get the same result. And for classical diffraction theory, like this decomposition theory has been in use since 1970s. Is that like, let's say for a given plane throughout the propagation axis, let's say you take the slice, and then at that slice, if you decompose your beam into this coefficients, then you can basically find your E field far away. And you might be obstructing or like imposing some aperture, or like using, or your beam might be interacting with turbulence, such that like any spatial mask, a beam which is being affected by any spatial mask could also be decomposed, and such that like the this between input and output LG coefficients, you can find this, you can define this tensorial elements. And for finite set of modes, and then like also finite extent on spatial mesh grid, this just turn to become like this matrices. So basically you have your input beam modes, and then like your obstruction, your turbulence, your whatever, basically just linearly transforms it into this output modes. At the same time, this basically transforms like this input coefficients into output coefficients. But like some other ABCD elements, such as your length, is basically acting on this input parameters, like such as the beam waist and then focal position, and then without changing these coefficients, they are changing it. I mean, I told you it's going to look ugly. My hand drawing is very bad. Like, let's say you have some input beam, and its coefficients is passed through like some spatial mass. You get like output coefficients, and like any ABCD matrix just changes its coefficients. Yeah. And as a result of like this mode decomposition, you can write any aperture or any field interacting with spatial mass is like is a combination of these two fields, which is the first one is like basically interacting with this diagonal elements of like this transformation, which is basically each mode being attenuated, and also the rest basically scatters these input modes into like various other output modes. That's why you can write them as such. And having said that, I'm particularly interested in like the self-healing type paraxial beams, such as Bessel-Gauss beams. Bessel-Gauss beams are one kind. They are limited diffraction beams. That's why, like, as they are propagating for a distance, like they stay more or less collimated, and up to some distance. And also, like, if you obstruct, let's say, some part, either centrally or like non-centrally, in some field, in some region, you will see that it's going to be healing itself. And you can generate this BG type of modes, for example, by using this axicons, which are just conical lenses, or like using this infinitely thin apertures. And so what I found is that, maybe I go a couple slides first, further first, is that like for modes which are higher order in P, which look more or less like a bullseye pattern, once they hit by an obstruction, they see the same amount of attenuation. That's why this beam interacting with some obstruction can be written down as like the input beam, which is being attenuated by a factor, plus a complement, an error term. And since this complement error terms are like
You mean
these.
a complement.
The complement. Yeah, not the, yeah.
This is, you look very nice today, Onur.
Yeah,
That's
yeah.
a very nice compliment. There's an E in that one.
Yeah.
Okay.
This was a
Don't
nice.
publish it with the I.
Yeah. Thanks for the compliment.
There's a nice compliment.
Yeah. And so, as a result, I mean like this complement term, since it's being composed of like this higher order terms which scattered away, and then these higher order terms are diverging with a rate of beam propagation factor. So with a factor of beam propagation factor, like they diverge faster. And that's why, maybe I could write it like this. So let's say before going to Bessel-Gauss beam, just for looking for like the high P order LG mode, like LG 020 mode. Even for that, you see that like once you implement an obstruction, it just splits into this attenuated original beam times the plus the complement. And as it propagates, even though this stays relatively the same, even though it just gets spatially larger by a tiny amount, the complement diffracts away super fast. Yeah, the complementary.
Find and replace.
Yeah, I mean, over here, in this portion, like this small portion, like it was carrying like 50–60% of energy, but as it propagates, just suddenly, bam, like just now inside this, there's only like 3 to 5% of energy. But for this, it stays relatively the same. That's why, as a result, if you are only looking for this inner portion of the beam in this subdomain, you will see it's healing itself because you basically offload this chunk, you externalize your complement beam.
So now the color scales are to indicate intensity, right?
Yeah, because these
Bright
are,
is
yeah.
high intensity. So those scales can't possibly be the same on all four, are they?
No, I should have been careful about it, yeah.
Yeah. So the light, the blue there,
Mm-hmm.
might be an order of magnitude dimmer on the other scale.
Yeah. I didn't put a color bar here.
Okay.
But yeah, I mean, long story short, like this is just basically like this energy is externalized for this complement. But
So what I'm getting at, when you
yeah.
do the self-healing, it's pulling in energy from these outer wings and doing the self-healing, but the energy is not infinite, as
Yeah.
you know, and so it gets dimmer. So you
Exactly.
reproduce it, but at some point you're not going to be able to see it.
Yeah, it's attenuating by this factor of like beta, which is just this B matrix diagonal element.
Okay. But if I was to plot this on the same scale as that, you wouldn't be able to see it, I bet.
Yeah, true.
Okay.
Yeah, fair.
That's not a compliment.
Yeah, and as I told you, like for example, like some other type of self-healing beams, such as Bessel-Gauss or like circular air beams, are composed of just real element sum of like all this, all this higher order modes. For example, for Bessel-Gauss, it's from 20 till 50, and then like for over there, like the attenuation experienced by each mode is more or less the same. It was like 92% or something like that. That's why, and you can see it from here, like for example, this red one is your input Laguerre-Gauss indices, or not indices, or coefficients. And they each get attenuated by 92%. At the same time, like some of the some other modes of the complement is just scattered away. And that's why at the end, for the intensity pattern, like you see like inside some self-healing subdomain, for example, if you look only within a disk near the propagation axis, you see that like this in the intensity pattern, like this terms looking like terms involving E just going to 0. And that's why if you use any similarity metric between unobstructed original beam and the obstructed and yet reconstructed beam, you find that you can use, like we used in our previous work, correlation coefficients, or like some other people use Lebesgue integral cosine. We find that like at the end, like it healed itself and then they look more or less the same. For example, this is the case for Bessel-Gauss. So your original Bessel-Gauss beam, you obstruct it, now it has this hole in it, and then like it is now, you can think this as like being separated out into attenuated original and the complement, and then again the original part didn't diffract, yet this complement just diffract super fast. Another reason why this diffract is super fast, because like smaller the beam you have, it will faster the diffraction you will see by quadratically, because Fresnel number is a power of W squared. For example, this is from our previous work. In our previous work, we generated by using some nonlinear process some sort of bullseye pattern looking like beam, and in that one too, if you are only focusing for the inner part of the field, it will the unobstructed beam will be going up to some point, to Z max, and over there it will start getting decollimated, and at the exact same spot your obstructed yet reconstructing beam is fully reconstructed itself. And in our work, we find that distance is exactly the Rayleigh range of the underlying LG beams. Yeah, so they exactly heal themselves at the underlying Rayleigh range. And so is the case for the this combination beams, such as like Bessel-Gauss, circular, Airy, whatever. And having said that, let's say I were to use this self.
Familiar.
Yeah, it's this is the work from folks in LSU, in particular Nick Lenning, that he graduated. And so I used this formalism of semi-classical formalism first to compute the how the generated conjugate and amplified probe beam would look like. And in this case, I'm talking about a four-way mixing process. In this process, like this is a double lambda process. We annihilate two pump photons, this green arrows, and as a result, like we generate a probe photon and a conjugate photon. So it's under the parametric approximation, it's Hamiltonian, looks something like that. But the nonlinear polarization of this two photon resonance process looks something like this. Again, like you, for let's say you are generating a conjugate photon, and to do this you annihilate two pump photons, and you are at the same time generate a probe photon. And this is, by the way, under first-born approximation of nonhomogeneous Paraxial Maxwell-Schrodinger equation. And to do so, the computation looks something like this. Let's say this is this chi3 being your, and then this is the z-axis. Let's say this is your nonlinear medium, and then like your pump square beam profile, 3D beam profile, as well as your probe beam profile, like probe star beam profile, overlap within this medium, and then you quantify this overlap by calculating this mode decomposition at each slice, each of these planes, and then like integrate over them. So, and at the end, like it gives you how much these beams overlap inside this nonlinear medium. And this new LG parameters tells you how your generated conjugate and or generated probe beam looks like. So for example, this is one of the preliminary results. Let's say I have like this BG beam. I obstruct this to the side of, to the right of your propagation axis, and at the end, like as it travels, like it healed itself, even though it loaded its, it offloaded its problems to the side, and let's say this is your obstructed beam LG indices, and like because of this non-axial obstruction, like basically you have like now all this you have now this OAM contributions as well. But once you focus into the center in the domain, you end up with this bullseye pattern. And another paper that might look familiar to you. This is also from LSU folks. Now, I also used this quantum theory for these nonlinear systems as well, for these multi-spatial mode nonlinear systems. In the case of spatial structured pump, I calculated squeezing parameters through this integral. Basically, in that case, again, like you have your pump spatial profile, the 3D, just like I showed you before, and then your you use like Gaussian probe, and your vacuum conjugate also come out as Gaussian, because we, in a sense, like by seeding this nonlinear process, we structure the density of states of the modes that are interacting. Even though, like in the vacuum seeded case, you would be having like all these contributions of all these plane wave contributions of the modes, but since the seeding vacuum conjugate will be mimicking our probe seed, I think we are justified to use this. So for the unobstructed and reconstructing self-healing beam structured pump and Gaussian probe and conjugate, Gaussian probe and conjugate seed, I calculate squeezing matrix elements, and but with only one difference, with only one caveat from the paper is that like our process is a seeded, like it's parametric phase-insensitive amplification process. That's why I'm taking this input beams Laguerre-Gauss mode indices as coherent state amplitudes. In that case, I mean, for example, I'm trying to find how much any of the quadratures are squeezed. Then you are basically calculating for like some sort of you are making a calculation involving like this operator algebra, and then your probe, your conjugate is vacuum, but your probe is now displaced to being a coherent state. As a result, you have like parametric phase-insensitive amplification. But it doesn't change it. Yes?
I mean, S3 is an element of some algebra, or?
Yeah, this SC is, sorry, I might need to take a step back, is you have, let's say, this interaction Hamiltonian, okay, right? And then like it is like quadratic in this creation and annihilation operators. And the power term in front of them, like the factor in front of this, is this chi1. And if you integrate it, you get the 3D version of this chi. Like, so basically overlap of all the modes.
The chi there, it's not even a vector, it's a tensor, I think.
I mean, yeah, it's usual tensor. It's tensor, but for this case, it's only just 1D because I'm only looking for structured pump, while everything is just fundamental mode. And so this is basically the power of this interaction between this chi3 nonlinear interaction, of this chi3 nonlinear interaction. And if you if you integrate this to get unitary time evolution, this chi basically is like, sorry, this xi is basically gives you this unitary evolution.
Some propagator or something. Okay.
Yeah, this is a unitary evolution, unitary time evolution operator.
Okay.
And then like that's why like now this is in Heisenberg or like Dirac picture.
Yeah.
It's a multi-dimensional squeezing operator.
Yeah, that's right. Exactly. And yeah, and squeezing, if you're not familiar, is that let's say you have I mean easiest example. Let's say you have momentum and position. The more you know about the momentum, the less you know about the position. Like it's over there, like you are squeezing the noise. And like for the light, it's for example, the more you know about the amplitude, the less you know about the phase or whatever. Another ugly looking figure.
So maybe like 1 or 2 more minutes. We're
Yeah.
out of time.
Sure. As I told you, like so, my both our previous experiments and like my simulation like models this system in a sense that like we have this our nonlinear medium, which is like this hot atomic vapor, and over here we are driving this process with this self-healing beam, either unobstructed or obstructed and being reconstructed, and also you are using this vacuum seed is the fundamental 0, mode, and you have like your vacuum conjugate, and they are interacting with the cell. And then like this, I assume this cell is from z equals 0 till the Rayleigh range of the fundamental LG mode of the self-healing mode. And what else? And as a result, so you generate this amplified probe, or like you create this generated conjugate beams, and this overlap leads to this squeezing, right? And sorry, and like I'm obstructing the beam right before the entrance of the cell, right before the chi-3 nonlinear process starts happening. So for the case like when I use 0.1, when I use both small probe and pump beams, then I don't see that much of squeezing. So for unobstructed beam, I see like 0.83 dB of squeezing and like 0.91 dB of squeezing, and the beams look like this. The generated beams look like this. Even though they show some signs of like this bullseye pattern, they are lacking most of it, and then like this is how their LG coefficients look like. A similar one for like smaller pump and slightly larger probe, as well as like a smaller pump and a very large probe. But once you have intermediate size pump and the small probe, I find that a really Bessel-Gauss looking kind of generated mode, and as well as like the self-healing mode. And as well as the generated mode also shows self-healing, and I saw up to 5 and 4 dB of squeezing for both unobstructed and obstructed beams.
All right. I think
This is all theory.
Yes, all theory. Yeah.
so. We need to wrap it up here. So
Yeah.
I mean.
Yeah. This by the way, this is
Okay.
just this.
Okay.
And then it gets smaller when once they are the same size. Gets smaller and smaller, and like once it's to the 3 and 1, we lose it again. But like for the sweet spot, we get like up to 5 and 4 dB squeezing. Yeah. And so to sum up, we use LG or HG modes as like the fundamental building blocks of like this multi-spatial modes, because pixels are not physical. This is the fundamental building block for this. And also like we feel like high P order, like this bullseye pattern looking modes or combination of thereof, then they can be factored out, the obstructed ones can be factored out, such that like we know the complement will diffract faster and our beam's going to yield itself exactly at the Rayleigh range. And if we use this to pump a nonlinear process such as four-way mixing, we see that like smaller probe beam will be exactly focusing at the center and leading to squeezing of both unobstructed and obstructed beams. And for the future work, I'm looking for spatial structured probe beam as well, and then like different obstructions such as turbulence, and different self-healing beams, and I'll be doing some optimization and also looking for multiple pump scales. So thank you so much.
All right, let's thank Onur again, and since we're running a little behind, we'll just if you have any questions, maybe ask them after the session.